Ever heard of a chip with zero silicon? Engineers just created the first functional processor without a single atom of silicon. And it's not just working. It might be the fastest, most efficient chip ever built. This could change everything. Section 1. When electrons pass through walls. Chip miniaturization has reached a critical point. Today, we're operating at 3 nanometer scales. Soon, 2 nanometers. Then what? Less than that. But there's a problem. At this scale, traditional electronics starts breaking its own laws. Literally. The transistors, those tiny switches that turn signals on and off in chips, have gotten so small that they've started behaving like quantum systems. And that changes everything. Imagine trying to close a door, but the wind keeps passing through it anyway. That's what happens with electrons. They start to tunnel. A phenomenon called quantum tunneling, where particles pass through barriers that should technically be solid. It's like walking through a wall. When this happens inside a chip, control over signals is lost. Currents leak, data scrambles, and performance crashes. This quantum limit threatens to silence silicon. No matter how much engineering advances, nature is putting on the brakes. That's why scientists started looking for something new. Something that doesn't just replace silicon, but opens completely different pathways. And that's when an old friend from the periodic table started to shine. Section 2. The iridescent crystal that could replace silicon. Its name is bismuth. At first glance, it looks like a laboratory decoration. A heavy metal with bizarre geometric shapes and an almost psychedelic shine. But behind this eccentric appearance exists atomic behavior that defies everything we know about semiconductors. Bismuth has a rare property, extremely strong spin-orbit coupling. Translation. The spin of electrons, a quantum property that works like a direction of rotation, is intimately connected to their movement around the nucleus. And this opens doors to something revolutionary. While silicon controls electrons only by charge, bismuth allows control of spin as well. This changes the game. Now, instead of simply turning a current on and off, we start talking about quantum processing at chip scale. It's the kind of feature that could give birth to new types of transistors, memories, and even qubits. But there's a problem. Bismuth, by nature, has no band gap, and this makes it behave like a metal. Without a band gap, there's no switching, and without switching, there's no computational logic. End of the line? Not exactly. Because there's a solution: doping. Adding chemical elements to bismuth to alter its electronic structure. And that's exactly what a Chinese team did, creating, for the first time, a functional bismuth-based semiconductor. Section 3. The first silicon-free chip in history. The feat happened in a laboratory at Peking University, documented in a study published in Nature journal. There, researchers took bismuth, already doped with telluride, and built, layer by layer, the first functional silicon-free chip in history. But they went further. This chip wasn't just a proof of concept. It was manufactured at the Ångström node, an engineering scale even smaller than 2 nanometers, entering levels where components are measured in units smaller than a silicon atom. To give you an idea, some parts of the transistor are only 0.5 nanometers thick, and that's exactly where silicon collapses. Because below 3 nanometers, quantum effects mess everything up. But with bismuth, these barriers seem to disappear. More than that, tests showed that this doped bismuth chip can operate at frequencies exceeding 500 gigahertz. While cutting-edge chips from Intel, Apple, or Samsung barely pass 5 to 6 gigahertz, this new prototype already surpasses 500. And it doesn't stop there. It also consumes 3 times less energy and has 40% faster switching speed. The comparison data was done with real transistors from Intel, TSMC, and Samsung. Section 4. Graphene, the invisible wire of the new generation. But bismuth wasn't alone in this turnaround. To interconnect the transistors of the new chip, engineers used graphene, the thinnest, lightest, and most resistant material we know. a conductor so efficient that it allows the creation of microscopic connections with practically negligible losses. The result? A chip completely free of silicon, with bismuth transistors and connections made with graphene. Each layer built with atomic precision, every detail designed for the post-silicon era. But manufacturing this is another story. In the architecture used, called gate-all-around, the transistor channels are completely surrounded by the control electrode, which requires millimeter-precise engineering. Imagine building a sheet 0.5 nanometers thick, then wrapping it in another equally thin sheet without even being able to see the underside. This level of precision was only possible by alternating layers of bismuth and graphene, one on top of the other, until stacking 4 transistors in a single block. And to not compromise performance, everything was mounted on a silicon base only as mechanical support. No active part of the chip uses silicon. It's like watching the birth of a new type of electronics, where the colored crystal and pure carbon replace what moved the world for decades. Section 5. The new chip race has already begun. The tests left no doubt. The bismuth chip surpassed the planet's largest manufacturers on 3 critical fronts: speed, energy efficiency, and electrical leakage control. These 3 variables define the future of processors, and more than that, they define who will lead the next digital revolution. And in this game, China has already taken the lead. The pioneering study came from Peking University, but there's more. China holds more than 70% of the world's bismuth reserves, a resource that, until now, was just curious and now becomes strategic. In other words, if this type of chip gains scale, whoever controls bismuth will control the next leap in computing. It's no coincidence that giants like TSMC are already moving. In partnership with MIT and National Taiwan University, TSMC has also started testing bismuth as a contact material for next-generation transistors. This shows the movement has already begun, and there's no turning back. In fact, this type of turnaround, based on new materials, has always been the pattern. It was like this with copper, with silicon, with germanium, and now with bismuth. Section 6. The post-silicon era has begun, but it's still in the lab. Despite all this progress, we're not yet talking about a consumer-ready product. The bismuth chip is a prototype. It works, it surpasses benchmarks, but it still depends on an entire ecosystem that isn't mature. Producing high-purity doped bismuth, creating layers with atomic precision, aligning graphene on an industrial scale. All of this is still far from the robustness of silicon's production chain. While silicon has decades of standardization, dedicated equipment, suppliers, refining infrastructure, and optimized factories, bismuth is still crawling. Adaptation would require new machines, new processes, and possibly new factories. All of this costs money and time. But the signal has been given. And like every historical transition, this one will also start small, academic, slow, restricted to research centers and military prototypes, until suddenly someone finds a way to scale. And when that happens, market logic will change with the same force it changed when we left the vacuum tube behind and embraced the transistor. The question is no longer whether we'll replace silicon. The question now is, who will be the first to transform this technology into industrial hegemony? Payoff. The future is being written in crystals and atoms. Bismuth, graphene, vertical architectures, frequencies exceeding 500 GHz. We're no longer talking about gradual evolution. We're seeing the beginning of a new paradigm. Just as silicon replaced germanium and chips replaced vacuum tubes, this new generation of materials could open pathways we can't even predict yet. Faster chips, thinner, smarter, maybe even more conscious? But no revolution happens alone, and no technology is born perfect. Bismuth's success now depends on something bigger than the laboratory. It depends on industry, investment, engineering, politics, and time. And perhaps, as in other great turnarounds, it also depends on who is most attentive when the market's tectonic plates start to move. Now tell me, do you think silicon can last another decade? Or are we already watching the birth of its replacement? Drop your opinion in the comments below, and if this video gave you a new perspective, hit that like button and subscribe to keep up with technology that's reshaping our future.